喂，Hello， 大家好。那在这场议程呢，是由我们卡巴斯基的全球威胁研究团队的 George 替我们来分享 IDA Pro 的插件。那大家都知道说，在近年来，因为做恶意程式越做越复杂，为了能够有效绕过现代的防毒软体，那所以在这场议程 ，George 他们的团队设计了今年 IDA Pro 就是第1名的插件，在 IDA Pro 全球插件市占第1名，然后有破1000颗星的开源插件，教大家怎么使用 IDA Pro 他们自己设计的插件，能够有效的自动化、快速的分析最困难的混淆问题。那让我们掌声欢迎 George。
Hello everyone, my name is Georgi Kocherin, and I'm a security researcher at Kaspersky's Global Research and Analysis team. And as part of this team, I investigate complex cyber threats, malware developed by state-sponsored actors such as Turla, Lazarus, or APT41, and many others. But apart from investigating malicious attacks, what we also do in our team is develop a set of open source projects designed to make threat research a simpler, faster, and less tedious process. And as part of these efforts, we develop a plugin for the IDA Pro reverse engineering framework, which is used by many analysts around the world. And the name of the plugin is hrtng, which stands for Hex-Rays Tools Next Generation. This plugin is sort of a multi-tool which implements more than 40 features useful in analysis of compiled code, especially malware. However, before I tell you what these features are, let me first talk a bit about the history of this plugin. Its development started back in 2016 when my coworker, an experienced reverse engineer Sergey Belov, forked an open source project named Hex-Rays Tools. And that's why the name of our project is Hex-Rays Tools Next Generation. And over the years, this internal fork has been receiving many features. These were features that we were lacking while doing reverse engineering of complex malware. We were adding them over the years to speed up tedious tasks that we had to do every day. And in 2024, we finally published the source code of our plugin online on GitHub under the GPL-v3 license, which gives the community the right to copy this code, modify it, and publish the changes made. And after we published the code, we have as well submitted the plugin to the annual Hex-Rays plugin contest. And this year, it was announced that our plugin scored first place. And today, to demonstrate you how hrtng can be helpful in your daily reverse engineering routine, I would like to analyze, together with you, a sample of a commercial spyware called FinSpy. Its use cases were first observed more than 15 years ago, and this spyware is notoriously known for including lots of obfuscation, which makes code very difficult to analyze. It's available from many platforms, from Windows and Linux to Android and even old BlackBerry phones. However, today we will be analyzing a Windows version of this sample. So let's get started. So over here I have the folder with the sample. And let's first view the bytes of our sample in a hex viewer. Hex dump -c sample and less. So if we look here, we can see that the first 2 bytes of our sample are 4D 5A. And these stand for MZ. And MZ, as some of you may know, is a signature of Windows portable executable files. So now let's open the file in IDA. I click on IDA, press OK, click on the Open button, FinSpy sample, and this is our sample. In this window, IDA asks us to choose the format of the file. However, it doesn't offer us to open the file as a Windows executable, only as a raw binary file. Since we have no other option, let's do this. We press OK, press yes here, and we'll need a little bit to wait until the auto-analysis of this sample finished. It'll just take a few seconds until IDA processes it. And now if we scroll down, we can see the first bytes of our sample. And when dealing with files that have an unknown format, well, what I usually prefer to do is just try to disassemble the first bytes of the file to see if they make valid code. Now, if I do this, I press C, and over here I can see that we have valid assembly code pop up. So in reality, our sample is not a Windows executable. It is raw assembly code, also known as shell code. And now that we have confirmed that these bytes are actually executable, let's mark that the segment with these bytes is executable. To do this, you press Edit, Segments, Edit Segment, and we tick all the permissions here: execute, write, and read, and press OK. And now let's start analyzing this code. We can see that the first two instructions of our sample are decebp and popedx. And if we examine the byte representation, we can see that the bytes of these two instructions are 4D5A. And these are actually junk instructions that are added to make the first two bytes equate to 4D5A, to disguise this shellcode as a PE file. And up next, we have two more instructions. We have the value 1 moved into the AL register and the value of EDX pushed onto the stack. Up next, we can see constants being assigned, this one to the ECX register and that one to the EBX register. And after this, we see these two instructions, FLDZ and FSTenv. And it may not be clear from first sight what they do. And to find this out, we can consult the internal documentation for the x86 architecture, which says that the FLDZ instruction is used to push the value 0 onto the floating point unit stack, while the instruction FSTenv is used to store the internal state of the floating point unit in memory. So this internal state that I was talking about can be represented with the following picture. And if we convert this picture into a C-style structure, it will look like this. So we can see, by looking at the code below, that after the malware executes the FSTenv instruction, it moves a value to the EDI register from the ESP-10 address. And if we perform offset calculation, as it is shown in the structure definition, we can find out that the ESP-10 address corresponds to the FIP member of this structure. And this FIP member contains the address of the last executed floating point instruction, the address of the FLDZ instruction. So essentially, after this code is executed, the malware will obtain the address of this instruction. Now, afterwards, we can see this loop being executed. It consists of XOR and roll operations. And since these operations are used in cryptography, well, we can say that this loop likely performs decryption. The key used for encryption is stored in the EBX register, assigned over there. And the number of bytes to be decrypted is stored in the ECX register. As for the bytes to be decrypted, the address is specified in the EDX register, which is calculated by adding the value 1D to the EDI register. And we discussed that the value of EDI is the address of the FLDZ instruction, which is 11. So 11 plus 1D, it equals 2E. And if we look at the address 2E, we can see that we have some junk instructions here, because it's an AND instruction containing some strange memory offsets. But if we undefine this instruction, we can notice that this data over here looks like something encrypted. So now we have the decryption algorithm and we have the data to be decrypted. And to continue our analysis, we need to perform decryption. This can be done in many ways. For example, you can write a Python script to do this, or a standalone C program. However, today I'll show you how to easily do it with the hrtng plugin, which already implements many encryption algorithms commonly found in malware out of the box. To use it, we first need to select all the encrypted data by pressing L+L, and then scroll down until the very end of the file. Then we press Shift plus asterisk to define this encrypted data as an array and press Enter. And then we right-click on the array and we select Decrypt Data. In this window, we need to specify the decryption algorithm to be used, which in our case is named custom. By the way, it's very easy to add custom algorithms to hrtng. To do this, you need to modify the decker.cpp file and add your algorithm to it in accordance with the examples provided there. In our case, the implementation of the algorithm takes just 3 lines. So, after we choose the algorithm, we also need to specify the number of bytes to be decrypted, which is filled automatically, as well as the encryption key, which was stored in the EBX register. We press OK here, and we click on Patch. And now we can undefine the array and convert it to code. And we have some valid assembly instructions here, which means that the decryption has been successful. So now what we have here in code is that we check whether the value of the AL register is 0, and if not, we make a jump. Remember that we saw the value 1 being moved to the AL register, which means the jump is taken to this instruction and then to this one. If we look here, we can see that these instructions are move EDI, push EBP, move EBP ESP. This sequence of instruction is well known as a function prologue, meaning these instructions here constitute a function, and we can define a function here by pressing P, and then decompile this function. And if we look down below, we can see this function being called. It is very interesting because its second argument contains a large number. And plus, we can observe that its return value is a function pointer, because as you can see, the value v32 here, this variable, is further used in code to call a function. So let's examine this function in greater detail. Over here, we can see that this function performs some manipulations with offsets, which are 0x3c, 0x78, and 0x7c. If you are a bit familiar with the structure of the Windows PE file format, you'll immediately recognize that these offsets are related to this format, because they are commonly used when parsing the PE file format. And plus, if we look down below, we see this function being called. And if we look at it, we can see that it executes a loop which involves manipulations with this constant over here. And if we perform a Google search on this constant, we'll find out that this constant is involved in calculating the CRC32 hash value. And so, we have a function that does both operations with the PE header and a hash calculation. And if you're familiar with malware analysis, you recognize that this combination of actions is commonly used to implement a technique called API hashing. It is a defense evasion technique which is used to stealthily call Windows API functions without mentioning their names in code. And let me tell you how it works. Let's say we want, for example, stealthily call the ntprotect virtual memory function. To do this, we calculate its CSE32 hash, and then at runtime, we iterate over all API function names provided by the operating system. And we calculate the CSE32 hash of each function. We do this in a loop until we encounter the hash value that matches the one we previously calculated, 5C2D1A97. And once we do this, it means that we have found our function, and then we can easily determine the address of this function and call it. And since this API hashing technique is very commonly met in malware, the hrtng plugin implements a functionality allowing to defeat it very easily. It implements many caching algorithms that are commonly met in malware, such as Metasploit, RO13, FMV1A, and many others. And let me now show you how to use it. So firstly, we need to go back to our function calls where these values are hashes, and then we need to import the Windows API type libraries into our IDA database. To do this, I press Shift 11 and then press Insert. In this window, I type MSSDK Win10, and another library we need to import NT-API Win10. You just need to remember these. And then we press Edit, Other, Turn on API hashes scan. In this window, we choose the hashing algorithm CRC32 and press OK. And now, if we press F5, we can see that the plugin renames the return value variables to Windows API function names. And what is more important is that it managed to assign the correct types and arguments of Windows API functions. This is very convenient because, for example, you don't need to perform a Google search to find out what the false argument of the NT-protect virtual memory function is. You can look it up straight in IDA. So, as you can see, this function performs some actions related to memory. And if we look down below, we can see this loop that involves a check for two signatures. The first one is MZ, we read this from the reverse, and the second is PE. These are the signatures. Well, they are encountered in the PE file format. They are the magic bytes of this format. And since this function deals with memory and the signatures, we can make an assumption that the malware, by executing this function, it loads itself by using the PE headers located in it. And indeed, if we look straight up, we can remember that these first two bytes are 4D5A, MZ, that was the first signature. And if we look down below, we can spot PE, the second signature, which demarks the start of the PE header. So now, what we need to do is to try and apply the PE header here to check that it is correct. To do this, I access the structure window and I press Insert. In here, I click Add Standard Structure and I type image NT headers. And now I go back to the bytes and press L+Q and apply the image NT header structure. And as we can see, the structure applied doesn't look like junk, it doesn't contain random data, and so we can say that we are dealing with a PE file header. So since the malware loads itself by using PE headers, to continue our analysis, we should do the same thing. Well, we tried to automatically do this using IDA, but we failed for some reason, because IDA only allowed us to load the sample as a raw file. And to perform loading manually, we need to do two things. The first one is map the executable file at the correct address. This address is called the image base address, which is stored inside the header. It is located under the image base field of the header, which equates to 400,000. And now what we can do is click Edit, Segments, Rebase Program, and we type in the image base value. And now we can see that our sample is now located at the base 400,000. The next step is more difficult. We need to find out what library functions from Windows are imported by the malware. This information is stored in the data directories of the header. Specifically, it is stored in the data directory with index 1. So if we look right here, we see many data directories. This one has index 0, and this one has index 1. And this value right here is the in-memory offset relative to the image base of the sample. This offset contains the input information. So to access data stored at this offset, what we need to do is add the image base, which is 400,000. We need to add it to this value 1240C. And by adding it, we get an address 41240C. And this is our import information, the byte storing it. But before we examine it, let me show you a trick that will help us avoid those offset calculations all the time. To use it, we go to the structures window and we expand the definition of the data directory structure. And here we press Ctrl R for the virtual address field and click Yes. In here, we make sure that use image base as offset base is ticked and we press OK. And now if we go back to our data directory, we can see that the address, the offset, now became clickable. And if we access it, we can see the same input information. Now, if we look at the PE file documentation, we can find out that this input information is an array of structures called image input descriptors. We need to import the structure into IDA to continue the analysis. I head to the structure window, press Insert, add standard structure, and type image import descriptor. And now we need to press L+Q to convert all these bytes to import descriptors. Remember I said that this data is an array of import descriptors. And we need to continue defining these structures until we see a structure consisting only of zeros. Which is this one. This structure contains only zeros and it marks the end of import descriptors. And now, once we defined all the structures, let's compare the defined structures with the actual structure of the import descriptors. By looking at the documentation, we can find out that the information about function names should be stored in the first field of the import descriptor structure. But by looking at the screenshot, we can tell that the first member of the structure is set to 0 for some reason. Well, the reason for this is that our sample does not actually adhere to the PE file format, because it is not a PE file, it is a shellcode, raw assembly code designed to disguise as a PE file. And what the threat actor did is that they tampered with the structure. They deliberately set this value to 0 to make it more difficult to analyze. And so the information about imports, this means it should be hidden somewhere else. To find out where, let's examine the non-zero fields of the structure, which is supposed to point to the library name and the section in memory storing resolved import function addresses. So again, these values right here are in-memory offsets, and let's use the same trick to convert them into clickable addresses. I select the import descriptor structure, and here I press Ctrl R for the second to last field of the structure. Click Yes, make sure use image base is ticked, and press OK. The same for the first sunk last member. Press Ctrl R, make sure we have a tick, and click OK. And now, if we examine the offsets here, we can see that the second to last offset contains the library name, which looks okay. However, if we look at the memory field that is supposed to store addresses of imported functions, we can see some strange data here. Now, if we start defining this data as 32-bit integers, we can see that the plugin starts converting them into Windows API function names. And the reason behind this is that we have a custom loading procedure here. These 32-bit integers are actually CRC32 hashes of API function names. And at runtime, well, the loader of this sample, it resolves each hash and overrides it with the function pointer, which corresponds to the function encoded by the hash. And notice how hrtng has been again able to automatically recover the arguments of this function. And now, after dealing with imports, what we can do is examine the entry point of this sample. The entry point, again, is stored in the header of the file under the name address of entry point. Again, it is an in-memory offset which we need to convert into a clickable address. Again, we use the same trick. Click on structures, expand the optional header 32 structure, which contains the definition of the entry point structure member. Press Ctrl R, make sure there is a tick, and press OK. So now we can click on this address and we can try to define these bytes as a function. But if we do this, we see that IDA colored the bytes corresponding to these instructions in red. This means it failed to define a function. To find out why, let's try to look at the function code. Over here, we can see that we have the registers ESI and ECX pushed onto the stack. And afterwards, we see lots of different operations, arithmetic ones, related to the ESI register, multiplications, bit shifts, etc. There are a lot of these operations, and if we scroll down until the very end, we can see that the ECX and ESI registers are popped back from the stack. Well, since the ESI register is popped from the stack, it means that the result of these arithmetic operations is essentially overwritten. This means that these operations are useless. And what we can do is replace them with the NOP instructions. And to do this, hrtng has a very convenient feature. What we can do is select all the junk operations and scroll until the very end, and then press Edit, Patch Program, Fill Knobs, and click OK. And if we look at what happens afterwards, we can see that we have a jump. If we examine the instructions located here, we can see these instructions: JA-GBE, JZ-GNZ, JO-GNO, etc. And we can note that we have pairs of conditional jumps here. And it is notable that these jumps, they branch to the same address. And furthermore, these jumps are opposite to each other, because let's say JZ is jump if 0 and JNZ is jump if not 0. And because one of these two conditional jumps is always executed, they essentially serve as one unconditional jump. This is an obfuscation technique which is designed to break IDA's disassembler. And to counter this technique and other techniques which work with control flow, hrtng has a feature called decompile obfuscated code. To use it, you need to go back to the definition, the start of the function, and press Alt F5. And then click OK. Now you can see that the plugin started analyzing the control flow of the function. However, the analysis returned with an error. Please make code, press Escape, and try decompile again. And the plugin shows us the code that caused problems. It contains some weird instructions which resemble junk. If we now look where these instructions are referenced by examining cross-references, we can see that this jump instruction branches to junk code. What is happening here? We see that the value of the argument is compared to the value of the EAX register, and in turn the value of the EAX register is calculated by XORing this register with itself, which, according to the properties of the XOR instruction, sets the register to 0, and then we add 1 to the register value, meaning we compare the value of the argument with 1, and if it's not 1, we jump to junk instructions. This is another anti-analysis technique because in a malicious environment, in a realistic environment, the value of the argument should be 1. And so what we can do, again, select these instructions, press Edit, Patch Program, Fill Knobs, because they don't anyhow affect the malicious behavior. And then we can try using the same decompile obfuscated code function to try and perform the compilation. Now, if we scroll down, we can see that we have some code that is at least readable. And now, if we try to research this code online, we can find out that it constitutes the engine of an obfuscator known as FinSpyVM. This obfuscator draws on the virtualization technique, which is very difficult to counter. And we won't be doing this today because if you're interested in how to combat virtual machines, you can read one of the many papers which specifically focus on the FinSpyVM obfuscator. And today we will be using a ready-made script which performs the obfuscation. However, there is an issue with it, because in order for the script to work, we need to specify we need to match the names of virtual instructions with their implementations. Let me show you how this works. Over here in the sample, we have an array of functions which implement virtual instructions. Let's say we examine this function. We can see that it does a shift left. And we note that this function is located at index 1 of the table. This is index 0, this is index 1, and it does a shift left. And in our deobfuscator, we need to mark that the shift left instruction corresponds to offset 1. I hope you understood what I mean. And essentially, what we need to do is to perform function recognition to find out what each function does, because manually analyzing each function it is very tedious. While IDA has a built-in function recognition engine called Flirt, it works with assembly, and because of this, it doesn't work very well with obfuscated code. However, hrtng implements its own function recognition engine called MSIG. It is based on microcode, and microcode is an optimized version of assembly used by the Hex-Rays decompiler, and because of this, it works better with obfuscated code. It's very straightforward to use. Firstly, you need to export function names from a sample that you already analyzed, and then you load the created signatures into another sample. Let me show you how this works. I switch into IDA, press File, Load File, MSIG file. I head to the M6 folder, and here I have a signature database. I import it into IDA, and then if I try to decompile this function, the plugin tells us that this function is a shift left. Similarly, if I decompile another function here, it tells us it is a JB. And since this function has an offset 2 in this array, we can say that the JB instruction has index 2. And we continue applying these MSIGs to the functions until we fill out this match between the opcodes and the implementations. We won't be doing all this process now because it takes a bit of a time, and we'll use a ready-made deobfuscation script. file, script file, and here I have the script. So now, if I go back to the entry point function and decompile it, we can see that we stumble on some malicious code, which imports lots of functions from Windows. These functions perform file management, like create file W, registry management, like enumerate value key. We also have functions working with window messages, like pick message A, and also we have a curious string here, SSL keylog file. And we also have some more curious strings, like here. If we scroll down, GNU PG home. So this is definitely some malicious code. And essentially, if we analyze the sample as we usually would do with any sample, we can tell that it is a spionage implant having many capabilities, from file system control to registry management and PGP key theft. And today, to get to this conclusion, we actually did many things: code decryption, API hashing analysis, function recognition, virtual machine deobfuscation. We did all these things very fast, and it all wouldn't have been so fast without the hrtng plugin, which helped us avoid hours of scripting and automate complex actions in just a few steps. And I hope that by showing this demo to you today, I've managed to convince you that the hrtng plugin can be really helpful in your daily reverse engineering routine. And so I encourage you to download the plugin using this QR code and try using it in your work or studies. And before I answer your questions, I would like to say a huge thanks to Sergey Belov, who is the creator and main contributor of the hrtng plugin. Thanks a lot, and if you have any questions, I'll be very happy to answer them.
喂，好，那时间看起来还够，开放2个问题。那有问题的话，有会众想要问问题的话，都可以直接用前面的麦克风。这边有一个同学，对，前面的麦克风。
Hi. Based on the functionalities of hrtng, I believe many of these were previously implemented by other plugins already. So, like for example, the COM helper, I assume that's similar to i.com, and the struct creation, I believe that was done by Hex-Code Explorer, and the hash one was previously done with HashDB, I believe. So, what I want to ask is there like to what extent does this plugin like how far do you want to develop this plugin? Like, it seems like it's like a lot of things all together in one.
Yes, thanks a lot. So about the fact that some of the functionalities are implemented in other plugins, yes, we explicitly mention this on the GitHub page, and the idea is you just not look over the internet for different plugins. You just download one plugin and you get what you want. You get one multi-tool for malware analysis. So if you're searching for something unique, I recommend you check the control flow unflattening feature, which can help defeat the OLVM obfuscator used in many malicious campaigns. And back to the original question, how we want to develop it. We want to develop it so that it helps us automate routine tasks as much as possible. Well, also the reason why we kind of were implementing all these plugins already made, because many of the plugins for IDA are not commonly updated. So if you update IDA SDK, some of the plugins may break. And so what we have been doing over the years is taking the code of these old undeveloped plugins which were abandoned and making them work with the latest versions of the IDA SDK. That was part of the development process, which is also difficult because it requires debugging some code. So we won't just, if we see some helpful plugin, we integrate it. Again, if the license allows, of course. So we just want it to be a helpful tool as much as possible, and that's the extent to what we do while development.
OK，那还有其他会众有想问问题的吗？有的话可以直接用你前面的麦克风。好，那如果都没有问题的话，那我这边问一个问题。I have got a question here, and because recently I have a reverse engineering about online game. It's some legend online game, and they using some kind of tricks, just like the malware using the control flow graph is very mass right here. So have you tried to using the faster CFG, the plugin feature, to solving the like VM protect the virtual machine? Is that challenging?
Thanks for your question. Well, speaking about virtual machines like VM Protect, yes, this is what we're talking about, right?
Yeah.
So it is done either dynamically. So what you need to do is just open the sample in the debugger and run it and dump the code in the hope that the code itself is not protected. This is very commonly happens in malware because virtualizing all the code makes it very slow. But if not, then you just, I don't know, use process monitor because there is no ready-made deobfuscator for VM Protect. If you have a VM protected function that is virtualized, I mean not the load but the code itself, then it's very difficult to analyze it statically. There is no solution on the internet that I know about that can help with that.
Okay, so 好，那我们在这边就是谢谢，再帮我掌声鼓励一下，感谢 George 今天精彩的演讲。